Good evening, everyone. Myself Nilmoni Karak, a research scholar at IIT Kharagpur, and I'm the PMRF NPTEL TA for the course Fourier Analysis and its applications. Okay, so today we will discuss whatever we have done in last week, and this is the week 11. And yeah, so and after that, after recalling everything, we will solve some problem which helps you to solve your assignment problems. Okay, so first, um, yeah, so we will discuss some uniform convergency of a Fourier series, and then I will discuss Dirichlet's theorem on pointwise convergence at points. The function has one-sided derivative. You can consider signum function, then Riemann localization principle. Then when we consider f as a monotone function, and then we will use Bonnet's mean value theorem. Okay, so let us recall one by one. First, uniform convergence of Fourier series. Suppose that if R to R is a 2 pi periodic function. Okay. Also, you can consider continuous as well. Function. Then the Fourier series also piecewise smooth is considerable. Sorry. Piecewise. So we are talking for uniform convergence. So piecewise smooth function is needed. Then Fourier series of fx converges absolutely and uniformly to fx. Okay, so this is the uniform convergence of Fourier series. Okay. Actually, this is a nice application of Bessel's inequality which we established in chapter 2. Okay, so considering f dash, yeah, piecewise, okay, and we have some coefficients, and with the coefficient Fourier series coefficient and using Bessel's inequality, we will have the proof. Okay, so one can see the lecture notes. and convergence. Then let us discuss convergence of the Fourier series at points. This was in domain, okay, in R. So interestingly, so domain should be R to R, okay. So for every function you cannot apply this theorem. So now instead of whole domain, so we are talking about at some points, okay. Convergence of the Fourier series at points where the one-sided derivatives exist. Yeah, for this case, a large number of examples fall under this scheme, and the main point is that the with regard to convergence of the Fourier series at the specific point, the behavior of f at points far away from x naught and do not matter as long as f is integrable or minus pi to pi, and f is sufficiently nice in the vicinity of x naught. So yeah, now the theorem basically says, so the theorem, suppose that f is a piecewise smooth 2 pi periodic function on R. But instead of continuous on whole domain, we are taking at a point, sorry, which continuous at x naught, and also considered one-sided derivative exist at x naught. Then the Fourier series of f converges to f of x naught at the point x naught. Okay. So for this scheme, we cannot talk for like many functions. Like there are many functions which is discontinuous, only one-sided derivative exists. Um, in that case, so we have this theorem. We have this result. Okay. Now further, these conditions can be considerably relaxed. So in the above, so piecewise smoothness of the function does not require. So are not required. This condition is not required. Um, so, for example, we can consider trigonometric function. Okay, so let us see next theorem, localization principle. So f is 2 pi periodic function which is integrable on minus pi to pi, and fx equals to 0 on an open interval I, which is a subset of minus pi to pi, then the Fourier series for fx converges to 0 at all points of I. So from these we consider in particular if two functions agree at all points of I, then their Fourier series behave alike throughout I. Okay. Now if we have jump discontinuity, then what we have? So next theorem, suppose f is piecewise smooth on and has one-sided derivatives at x naught and a jump discontinuity there. Then the Fourier series of f converges at x naught to the value sorry suppose f is piecewise smooth on minus pi to pi and has one-sided derivatives at x naught and jump discontinuity there. Okay. Then the Fourier series of f converges at x naught and to the value this. Okay. So converges to the point this, converges to the function. Now we will see Dirichlet's theorem on for monotone functions. This is very important. Okay, some interesting properties are there for monotone functions. Okay, so let us recall them. A monotone function has only countably many continuities. Okay, so if f is monotone, then f must have only countably many discontinuities. Okay, the discontinuity set of a monotone function should be countable. And second, and these discontinuities, these discontinuities are simple jump discontinuity. Also, a monotone function is the Riemann integrable. What about the converse part of 1? So you have any countable set, dense subset, so dense is needed here, dense subset D. So for this there is a monotone function which is discontinuous precisely at points of t. Okay. And last, a monotone function is differentiable almost everywhere. Yeah, so we will see that the Fourier series of a piecewise continuous function, a piecewise continuous monotone function, is quite well behaved as regard convergence. Okay. So that is called actually Dirichlet's theorem for monotone function. Okay, let me mm, write this theorem. Very old theorem. Suppose F is a piecewise continuous monotone function. The Fourier series of F converges to fx at all the points of continuity and at a point. Yeah, so this is very trivial for continuity. So if it's a function from minus pi to pi and piecewise continuous monotone function, then the Fourier series of f converges to fx at all the points of continuity, and at a point of discontinuity x naught. So point is your x naught. It converges to and yeah, and what about mm, your boundary points? So at the points plus minus pi, Fourier series converges half so this is pi negative and plus minus pi positive. So to establish this, we need Bonnet's mean value theorem. Let us recall this. So first, G is any continuous function on closed interval AB. If AB to R is monotone, then there exists C belongs to closed interval AB such that FT GT dt. So f of b minus integration c to b gt dt plus f of a plus integration a to c g2 dt gt dt. And yeah, so if f is monotone and there exists c such that this, okay, and if f is monotone decreasing and if is positive non-negative, then f of plus a to c gt dt. If f is so for decreasing, so we have only this part, okay, and for decreasing, sorry, for increasing we have another part. Yeah, here f should be non-positive. This is called Bonnet's mean value theorem. Okay. And this useful mean value theorem, not mean value exactly, this is these are useful integral, okay. So first is your integral 0 to infinity sine omega t by t dt. This is w pi by 2 and the f is r is monotone any a is greater than 0, if u w u by u pi by 2 f of 0 plus so yeah, instead of like, so s can be infinity also. Okay. Also, these are useful to solve assignment problem. Okay, now we move to some another topic, temper distribution. So first we recall the Schwarz space. Okay, S of R. We already have seen previously, right? And this is actually a topological vector space. Uh, okay, we already have seen the properties for Schwarz space, and we have seen some examples of Schwarz space. So yeah, example means elements of Schwarz space. And okay, so in chapter 4 actually, yeah. So okay, let us recall the definition. So tempered distribution okay, sorry. So first Schwarz space, a sequence Fn in SR a sequence Fn in SR converges to F. This is also in SR. This difference goes to 0 as n tending to infinity. So one can check the vector space operation on SR. So sum and product, scalar product holds with this definition, and lambda f goes to so this is a topological vector space. Okay. Okay, let us see continuity of differentiation. Now we will recall if f is in SR, then f dash is in SR. Okay, so the simple actually mm, the linear operator f to f dash, this is continuous with respect to the topology on SR. And now the theorem is continuity of differentiation. The differentiation map on SR given by is continuous. One can check the proof from lectures notes or video. Simple proof. Now continuity of the Fourier transform. So we already have seen that the Fourier transform maps SR onto itself, right? So this is continuous with respect to the L2 norm. Okay. The theorem is basically SR is continuous with respect to the topology of SR. Previously we have seen this. Now we are ready to study the definition of tempered distribution. So a tempered distribution continuous linear map SR to C the set of all such continuous linear maps denoted by letters R is a vector space known as the space tempered distribution. The space of tempered distributions is called S dash R. The set of all such continuous linear maps. Okay. Because the direct delta function and its close cousins, the direct delta function consider the map delta naught SR to C given by F to F naught. and this is linear actually and continuous with respect to the topology on S address. From the definition. Okay. Also, second example, suppose qx is a polynomial and f belongs to SR, then qx fx is an element in SR in SR and so is integrable but is this linear and continuous? How to check the linearity? Linearity is simple. So we need to just check so linearity leads this. Okay, let's to do this in implies that dx goes to 0. So first let degree of qx is n and rx take 1 plus x squared to the power n qx. Then the convergence of Fn gives us supremum R next Rx to 0. Now Qx time Fnx dx, this is less equals to Fnx this is supremum R mod Fnx Rx is an outside and goes to 0 because of this ascending to infinity. Not this, like so this is bounded, so goes to 0, and because you already have seen this goes to 0, so total is bound, so it goes to 0, total goes to 0. So finally we have we just discussed another example. Okay. Oh, we have one more example. Yeah. So this is 2, right? So use this. Defines, say this defines a tempered distribution. Okay. Then also any like we can consider classical functions regarded as distributions. So this type of function is also like, delta does S up to C given by minus f dash 0. This is a tempered distribution, derivative of direct delta function. Sorry, not direct distribution. And suppose U is a tempered distribution and Qx is polynomial define Qx and U to be the map set to C given by this is a tempered distribution. So any tempered distribution is given U and consider any polynomial Qx, then the U of Qx comma Qx f f goes to U of Qx f is again a tempered distribution. Also examples: cos e to the power x, sin e to the power x are tempered distribution. Okay, these are whole content we have learned in last week and next we will see the applications of this tempered distribution, Fourier transform of tempered distribution. Okay, and support of a distributions, Liouville's theorem, and last convergence of distributions, and at the end we will see Poisson summation formula. This is very crucial in number theory as well as in different area. Okay, now let us solve some problems. Okay, so I'll start in 2 minutes. Okay, so let's start. Given that yeah, consider D equals to the set of discontinuities of F 0 1. Then D can be Q, D can be Q complement, D can be Cantor set, D must be discrete set, the function integrable. Okay, so this is very easy actually. Initially we have seen a monotone function has only countably many discontinuities. So has only the countable, must be countable set. Okay, so this is possible, can be, this is true. This is not possible because this is uncountable. This is not possible because this is uncountable, and the must be discrete. So discrete means maybe n, not always discrete. So it can be q. Okay, it can be rational. So this is wrong. This can be dense actually. So the function is integrable. Yeah, a monotone function is a Riemann integrable. Okay, so this is true. So A and E are correct. So consider the function given by x plus half. So the value of limit 0 to 100 if u sin omega u by u du. Solution. So let us recall the theorem. If 0 to r is monotone, then limit omega tending to infinity 0 to s. Oh, then for any s greater than 0, we already stated earlier. So here f is 1 by gamma x plus half. Okay, so this is f of x. So this is monotone decreasing. So monotone. And now, so s is, we can take 100. So then limit omega tending to infinity 0 to 100 f of u sin omega u by u du pi by 2 f of 0 pi by 2 gamma half root pi by 2. Okay, so this is done. And next problem, question 3. Which of the following is true? So we already have seen one theorem. Not theorem, the definition. These differences. So this actually goes to 0. So yeah. Yeah, so we will use this definition. So first, what is Fn? Fn is your exponential minus nx square, right? So this goes to 0 as n tending to infinity. Exponentially decay goes to 0, and this is obviously monotone. Okay, so now supremum are xk dl fnx minus dl fx. This is just supremum r xk dl, because f is 0, exponential minus nx square, right? See, now if we differentiate this L times for all k and L, so you keep just so yeah, the supremum we cannot get 0, because when like this is exponential decay, when we differentiate this with respect to x, so we have minus 2x additionally, and modulus is there, so no problem. So we have the power, we have the increasing power of x, okay, so repeatedly, and that doesn't that doesn't go to like 0 as for all k L belongs to n. So this is as also as n tending to infinity. Because this is not bounded as well. If this is bounded, then definitely so this is if and only if true, so this is wrong, converges. And similarly fn equals to exponential minus x square by n, and this goes to what? This goes to 1. So 1 is nothing, that is again 0, because supremum rx to the power k dl fnx minus dl fx. So this is 0, right? So this is one constant, 1 is constant, so this is 0. So this is, so again supremum x to the power k dl exponential minus x square n So condition, so reason is same as n tending to infinity. So here clearly this is not true for, so this is again not true. And what about this sin x hyperbolic x plus n? So this is 2 by to the power okay x plus n plus e to the power minus x plus n. So as n tending to infinity, this is basically zero, goes to zero, right? And now consider the soup r x to the power k dl fn x so this is goes to zero, right? So again so here so this is in numerator, okay, and won't be any problem. So as n tending to infinity, basically anything with exponential power, so this goes to always zero as n tending to infinity for all k l belongs to natural number. And similarly for d sin pi x by sin hyperbolic x plus see simply this is goes to zero because of this. And similarly, so you consider soup r dl, so x to the power k dl sin pi x sin hyperbolic x plus n. Still this goes to zero because this exponential power, so anytime like dominate anytime any power polynomial, and this is in numerator, it's denominator, so always goes to zero as n tending to infinity. So again this is bounded, and as n tending to infinity this goes to zero, okay. So this is also true. Okay, let us see next problem. Question 4. True or false? Ether is dense in LPR formula is equals to P infinity. This is simple actually, from lecture you can check. This is false because ether is dense in LPR for not in there. So false. So question 5. The set of all smooth functions with compact support dense in SR. This is actually true. Okay, so this is true, and previously this is true. So combining them, this is true. So this is like dense in LP, bigger set. So dense in any subset of LPR, right? Yeah. Consider the function this is sine. Extend this as 2 pi periodic function on R. The sum of the Fourier series of the function fx at the origin equals to. Okay, so you have a function, and first extend this as a 2 pi periodic function on R, and the sum of the Fourier series of the function fx at the origin equals to. So this converges. So here basically we have to use Dirichlet's theorem. Okay. Dirichlet's theorem. So here, so at origin, so the sum is basically f of 0 plus f of 0 minus. So by Dirichlet's theorem, so at 0 this is discontinuous. Not this. Yeah, this is discontinuous. If you check the continuity at 0, this is discontinuous. Mod x is there, so upper right hand limit 1. By Dirichlet's theorem. And what is f of 0 plus this limit extending to 0 plus f of x minus f of 0, this is x minus 0, so limit extending to 0 plus sine pi by 2 mod x by x. So x is positive, so sine pi by 2 limit 0 plus, so sine pi by 2 x. So this is actually 2 by pi. And f of 0 minus, this is actually minus 2 by pi. So this is 0 basically. Okay. Okay, so up to this I have prepared for today, and yeah, we will meet next Sunday at 7 p.m. and we will have an extra class on probably on Tuesday at 3 p.m. Okay, I hope everything is clear for today. Okay, bye. Sorry, there is a mistake. So this should be here pi by 2, not 2 by pi, this pi by 2, this is minus pi by 2, still this is 0. Okay, thank you.